Welcome to Chapter 3, Part 1. We're covering acids and bases in this chapter, and so at least the first part of this chapter is a bit of review. You definitely covered acid-base chemistry in General Chem. And there's a reason why this review has its own chapter as opposed to all the review sections in Chapter 1. It's because acid-base chemistry is really important. We see acid-base reactions or reaction steps within more complex reactions throughout the year. And so we want to make sure that we really take some time to revisit that and to learn a little bit more about analyzing acids and bases. So at the beginning, we're just going to review some definitions. All right, so when we talk about acid-base vocabulary, there are three definitions, right? There's Arrhenius, there's Bronstedlowry, and there is Lewis. Now, most of the time when we just say the term acid or base with no guy's name in front of it, we're talking about Bronstedlowry. And that's important to remember. Most of what we will talk about in organic will be Bronstedlowry and Lewis. If you recall from Gen Chem, Arrhenius defined acids and bases as by their ions produced in water. An acid produces H plus in water, and a base produces OH minus in water. Now, this is great, right? This is better than defining acids and bases based solely on taste or, having to feel them. But this is really limiting. In organic, we are frequently not working with aqueous solutions. Many of your organic compounds aren't soluble in water. And so talking about acids and bases purely with their relationship to aqueous solutions doesn't really work out, doesn't give us enough room when talking about acid-base reactions, right, in organic solvents. And so as we go down this list, Bronstedlowry doesn't disagree with Arrhenius, it just expands the definition. And in the same way, Lewis doesn't change the definition of acids and bases, it just expands how we can think about acids and bases. So we get broader. Arrhenius is very specific, Bronstedlowry is a little bit more general. So now instead of thinking about it in terms of what they produce in water, now it's just acids donate a proton. Now remember, we talked about this when we talked about formal charges. A proton is a hydrogen cation. All right, so we see a lot of protons moving around in organic reactions, and so that is why it's important for us to review acids and bases, because whatever is donating the proton is acting as the base. Whatever is donating the proton is acting as the acid. Whatever is accepting the proton is acting as the base. All right, so now it can include Arrhenius acid bases. For instance, over here you see HCl and water, right? It's producing H plus or H3O plus, right? Whenever you have H plus in water, water picks it up and you get hydronium. So it still fits in Arrhenius, but it also fits in Bronstedlowry. The hydrochloric acid is donating the proton. The water is accepting it. All right, it's a Gen Chem example. A base, right, is going to accept a proton. So if we look at something like tert butoxide, right, this is our base. It is accepting a proton from the water, so now water can act as the acid. Water is, let's see, this is a good vocab word. Water is amphoteric. It can act as acid or base, depending on what it is interacting with. So with HCl, it acts as the base. With a stronger base, it acts as the acid. Another bit of vocabulary from Gen Chem is, what about the product side? Notice this equilibrium arrow here. So this is going back and forth. There is some equilibrium where there are products and starting materials present. The base accepted the proton, so it makes the conjugate acid, right? Because if we're going in the reverse direction, this alcohol is going to be what is donating the proton. The water, which was the acid, it donated a proton, forms the conjugate base of the hydroxide ion. So again, going in the reverse direction, the conjugate base, the hydroxide, would be accepting the proton. So you get these conjugate acid-base pairs in any Bronstedlowry reaction, right? Whatever is accepting the proton is the base, and once it has accepted the proton, it becomes the conjugate acid, right? So we call this an acid-base pair right here. The acid donates a proton and becomes the proton acceptor in the reverse reaction. So you have another acid-base pair. Now, we talked about curved arrows when we looked at resonance. When we were talking about moving between resonance structures, those curved arrows were just tools. We know that the electrons weren't actually moving because the reality is a hybrid resonance structure. When we used curved arrows in reactions, and we're going to be talking about this in really a lot more detail in chapter 6 and then for the rest of organic, but in chapter 3 we are introduced to it for the first time. It is showing us the actual electron movement. The rule of the arrow is the same. The base of the arrow, the tail, right, starts where the electrons are, and the head of the arrow tells us where it is going. This shows us bonds breaking and bonds forming. So if we start with the lone pair on the base, you're going to be forming a new bond to the proton, because remember, the base is accepting a proton. So the arrow starts at the lone pair and ends at the proton. Now, hydrogen isn't going to have two bonds, so that HA bond needs to break, right? The acid is donating the proton, so it breaks off from the acid. So you have to show what happens to those bonding electrons. Will they stay with the A, which ultimately will be the conjugate base over here? And so we are showing what happened to the lone pair and the bonding pair when this reaction takes place. One of the most frequent mistakes I see would be a base. If you're taking notes with me, don't write this down until you have a minute to check it. A lot of people instinctively want to go, oh, the proton is moving, and that's how I get BH and A minus. This is incorrect, right? You're never going to, when you have a proton transfer, there are no electrons coming with the proton, right? And since our arrow is supposed to go from electron density to where it is going, it's going to point at that proton, right? And then you would show that bond breaking. Okay. Here we go. If we look at a specific example, now we're looking at an example where water is not one of the reactants in the beginning, but it's still an acid-base reaction because we have a proton donor and a proton acceptor. You can see that the hydroxide is acting as a base because one of the lone pairs on the oxygen is forming a bond to the proton. And then, again, hydrogen's not going to have two bonds. So we show the bond, this OH bond breaking at the same time. So it is the base attacking the acid using a pair of electrons. All right, the acid's not just arbitrarily losing the proton, the base is taking it. Right? The acid-base reactions take place in one step. The base takes the proton and the bond to the proton with the acid breaks. That all happens in one concerted step. Now, this is something that is going to come up in the future. Multi-step reactions do occur. And we are going to learn a bunch of those this year. And sometimes an acid-base step just happens to be one of the steps, right? Here you see let's see. In fact, two of them are acid-base steps. We have the acid that is the hydronium and the base that is the alcohol. And then there's this interesting step here that is not an acid-base step. That's loss of a leaving group. We're going to learn about that in chapter 6. And then we have an interesting intermediate with a carbocation where water is now acting as the base and that intermediate is acting as the acid. I'm not going to ask you to do multi-step problems like this yet. This wouldn't be fair. We haven't learned enough. But it gives you a little bit of context as to why we need to discuss acid-base reactions, because they become small parts in larger reactions later on. All right, so for now, we're just going to focus on correctly using these curved arrows. All right, you're going to have some homework problems that will encourage you to use this skill. I have a practice set up, on eCampus that encourages you to use this skill. And if you go into your Wiley Access Plus, there are skill builder and practice the problem questions right there within it looks like 3.2 of chapter 3. The last thing I want to talk about in this video is quantifying acidity. So when we talk about acid or base strength, we can use numbers, right, to quantify the strength. That's going to be where we discuss pKa's. And then we can also qualify, right? We can qualitatively determine, I'm not going to use the word qualify, qualitative, there we go. And this is going to use structure. So if you have pKa's, well then you could stop here, right? The pKa is all you really need. We don't always have pKa's on every possible organic compound that exists. And so sometimes we need a qualitative determination of acid-base strength. That's what the next video is going to be about. We're going to review the quantitative analysis because that is something you learned in Gen Chem. And it is not going to be the focus. So we're just going to have a little quick review. All right, now quantitative analysis uses equilibrium constants and equilibrium equations. You are not going to be doing this math in this class. You already did that in Gen Chem, so we're going to very quickly review this. We know that when we talk about K values, equilibrium constants, we are comparing concentrations of product over concentrations of starting material. You notice H2O is left out because that would just be a 1. You can't discuss the concentration of water in water. So that gets left out. Now, Ka's are going to tell you about the acid strength. If they are larger than 1, it's a stronger acid, meaning that more of the acid dissociated. If it's smaller than 1, right, that means we have more HA present. so less of it dissociated, so it was a much weaker acid. Now, we use P functions a lot of times to make numbers easier to work with, honestly. And so pKa is going to, that P function is always negative log of whatever is following it. So then that would be the negative log of the Ka. When you do that negative log, right? So, oh, I'm sorry, this explains to it. I don't know what happens to some of the the characters when we put the PowerPoint in different, like putting it into GoodNotes messed up some of the like superscript and subscripts. But Ka values can be enormous or tiny, right? So they're saying like 10 to the negative 50 to 10 to the 10th. So the size of these numbers can be huge or really, really tiny, making it bulky to work with, right? Whereas doing pKa's, now we're going to be somewhere from negative 10 to 50, right? Much more manageable numbers to work with. But it also flips, whereas a really large pKa goes with a strong acid, a very small pKa goes with a strong acid, right? So smaller, let's make sure we note this, smaller pKa, right? The lower the number, the more negative it is, the stronger the acid. Right? Now, if you are given pKa's, then you just need to know this, because I'm going to ask you to compare different compounds and ask you which one's a stronger acid. If you have pKa's, you don't have to do anything else. All you need to know is this: the smaller number is the stronger acid. And anytime that you talk about acid and base strength, you're going to come across a table like this with a bunch of random acids. And you see, one of your strongest acids, H2SO4, up here at the top, negative 9 pKa. Ammonium ions, not considered very acidic. It has a pKa of a 9.3, right? So that's going to be much higher. You do want to note the relationship here. This is going to come up a lot in the next video. The stronger the acid, the weaker the base. And that makes sense, right? Because what makes a strong acid? A strong acid can donate or give up its proton very easily. If it can give that proton up very easily, then that means the conjugate base must be relatively stable without it. So it is not going out of its way to accept protons, right? Whereas a stronger base, right, maybe something like ammonia, which it's not a strong base, but it's a lot stronger than a, what is this? The conjugate base of sulfuric acid. It is more basic, so it's trying to get a proton to make a weaker acid, right? Because then once it has that proton, it's pretty happy to keep it. Now, we don't always have and here's just the extension of that chart. We get to some really basic, really basic compounds down here. We don't always have a table like this. We don't always have pKa values, right? There are millions of organic compounds. You're not always going to have access to pKa data. And so how can you solve problems without pKa data? And that is what we will cover in the next video. Okay, before we end this video, something that we are going to be interested in doing, whether we have the ability to quantitatively or qualitatively compare, is predicting equilibria. So we know that an equilibrium arrow means it is a dynamic reaction. There is some starting materials, there's some product. But which side is favored is what the questions in this, oh, good Lord, that was a very bad sentence. Okay. You being able to predict what is going to be in higher abundance is a possible test or quiz question. And if you have pKa data, then what you are looking for is the side with the weaker acid will be favored, right? The stronger acid and the stronger base are always going to be on the same side, and they are going to want to react more. The weaker acid, the weaker base, those are going to be more stable. So when we look at an example like the one on the slide, the tert butoxide base reacts with the acid, right? So we would have these reaction arrows to form the alcohol conjugate acid and the conjugate base. If you have the pKa values, that's all you need. The lower pKa is the stronger acid, and the higher pKa is the weaker acid, meaning it is more stable, right? So we can indicate that the products are favored if we make the forward arrow longer, right? So that's products favored. If we found that the weaker acid was on the reactant side, right, then we just flip that. The backwards arrow is longer, and that means reactants are favored. Just tells us which side the equilibrium lies on. So it's relatively simple if you have pKa's. If you just remember, lower pKa, stronger acid, equilibria favors the weak. Now, sometimes, so I just want to point out, on this slide, look, we are comparing 15.7 to 18. So the pKa's are somewhat close together. When we see reaction arrows that are just forward, there's no equilibrium arrow present, it's because the pKa difference is so large. It's not because there isn't an equilibrium, that there is just no original base and acid present at all, but it's going to be an insignificant amount, right? So we usually, there's a line there with the difference in pKa values. I don't grade you on using forward arrows or equilibrium arrows unless the question specifically asks for something like this. Which side is going to be favored? I won't try to trick you on that. And that will conclude part 1 of chapter 3. I will see you in part 2 for qualifying acidity using just the structure.